Today we want to finish our discussion of Green's theorem. Just wanted to remind you where we were. Last time we used Green's theorem to prove this interesting application. That under common conditions, the conditions of Green's theorem, so this has to be a piecewise smooth, simple closed curve enclosing a region with no holes in it. And then it turns out that the area of the enclosed region is equal to the line integral x dy around this curve, or it's minus the integral of y dx around that closed curve. We could show either one with Green's theorem by choosing different vector fields and just plugging them into the theorem. Furthermore, if you took 1/2 this one plus 1/2 this one, you got this one that's occasionally used. Sometimes it's nice to do this average of the two, right? So we have that result that we could actually evaluate areas of common regions by taking line integrals along their boundaries of certain ones, the integral x dy or minus y dx. And these are special cases of line integrals that just happen to give area. I'll put these notes up on later today, but here are my notes for that, and we'll just go through them then. Suppose, and here's the derivation we did before. This was the proof. Green's theorem, you use the fact that area is the double integral of 1 dA. So this is the proof. Maybe I'll just remind you. Green's theorem says that this integral is dx dx minus d0 dy dA, and then, but I'm sorry, this is the integrand 1 is equal to this, but this by Green's theorem is equal to integral x dy. So that's how you get that one, and similarly for the other two. Move the page down here. Let's find a formula for the area of an ellipse. This is my most fun application. This would be a terrible integral to do just as a double integral because the boundary is curved, right? Suppose you take the standard equation, x squared over a squared plus y squared over b squared equals 1 for an ellipse at the origin. Make it as simple as possible. It's still hard to do this double integral. We can evaluate it instead by doing a line integral along the boundary is what this says. So we can take the area and say it's by this formula here, it's integral x dy along the boundary. But remember how you evaluate x dy? You replace dy with dy dt dt and let t run over its values along the boundary. And you recall this for writing parametric equations for an ellipse. A circle, you can put x equal a cosine t, y equals a sine t for a circle of radius a. For an ellipse, similarly, you can put x equals a cosine t, y equals b sine t, and now you'll travel around the ellipse instead of the circle. It's easy to show this goes up on goes around an ellipse. Now to evaluate x times dy dt dt with this parametric equations for an ellipse, t going from 0 to 2 pi to go once around. We replace x with its parametric form, a cosine t. Then we calculate dy dt, where b is y is b sine t, its derivative is b cosine t. There's dy dt dt. And if we can evaluate that calculus 1 integral now, which is ab cosine squared, I'll pull the ab out, that will calculate the area. Well, that's not a hard integral to do cosine squared. Remember the trick? There are different tricks. You can use the reduction formula, for instance. But the easiest thing people remember is use the half angle identity, right? Cosine squared by trigonometry, the half angle identity is 1 plus cosine 2t over 2. Right? So if I can integrate 1 plus cosine 2t over 2, and I can, then I'll be able to evaluate this one. Integral of 1/2 is just 1/2 t. Integral of cosine 2t over 2 is just 1/4 sine 2t. The AB outside still multiplies. If you evaluate this at 0 and 2 pi and take the difference, you wind up with just pi AB. How about that? That just seems so natural what you get if you think about it, because if you had A equals B, this would be a circle, and you get pi A squared, right? Pi A squared is the area of a circle of radius A. When you have axes, semi-axis lengths of A and B, the area of the ellipse then is pi AB. Maybe you could have guessed that. But there's the proof, an application of Green's theorem. Then I'll mention this, but this isn't important for our test. I want to not do too much here. This also allows you to do centroids, right? By taking a double integral and using Green's theorem, we rewrote it as a line integral to get this area formula. Similarly, when you calculate a centroid, remember what a centroid is? It's sort of the center of area. It's the center of mass for a solid or a plane region of uniform density. So if I have a plane region, for instance, of uniform density, coordinates x, y, x bar and y bar have that formula, which was a double integral for computing the centroid. Because of Green's theorem, it turns out we can write it as these line integrals around the boundary. So I just wanted to point out that in some applications, it's nice to know that you can use a line integral to evaluate the centroid. All right, so don't worry about that formula, but I thought it was worth seeing. Here's some more uses of Green's theorem. Once in a while, you get an integral along a curve that's not closed, and so Green's theorem doesn't apply, but it's a hard line integral. What can you do? Sometimes you can cleverly use Green's theorem still to evaluate it, because what you can do is if you've got some terrible curve that's not closed, you can just take something easy to close it, like a line segment. Now it's closed, Green's theorem applies. If you can just apply Green's theorem to the nasty curve plus the easy curve, and then subtract off the line integral along the easy curve, you can get the line integral around the rest of the part that you wanted. Let me put an example up here. Suppose I wanted to take a line integral along this black path, which is from 0, 0 to 9, 9 to 9, 18 to 0, 27 of this quantity, sine x plus y dx. So suppose this is my line integral. I'm going to go along this curve in black, see. Oh, golly, what a mess. You know, that integrand is not so easy. It's not terrible, but it's not terribly easy. And I got to break up into 3 pieces, one here, and one here, and one here to be able to evaluate it. Maybe I could do it easier with Green's theorem by closing the curve, making a closed curve, that's the red one here, and then subtracting off this part, right? So that's what I'm going to do. I'm going to use Green's theorem to evaluate the line integral along the closed curve, and then subtract off one line integral along this boundary. Well, this is actually pretty easy for this problem, because for this integrand, if I call this f of xy equals sine x plus y, I plus 6x plus y, j. We can call the components little f and little g, or f1 and f2, we also called them last time. And we'll let this line here, so C is the closed curve, or C hat is the closed curve. If I call this C1 along here, what I want to do is take the line or integral around the whole thing, less the last part, and I subtract off the line integral here. Well, instead of subtracting off the line integral going this way, I could go the opposite way and add it, right? Because the line integral one way, remember, is minus the line integral going the other way. So that's what I'm going to do. I'm going to say that the line integral I want along C, this function, is equal to the line integral around the whole thing, C tilde, C hat I should have put, plus the line integral going up, which amounts to minus the line integral going down. So line integral around the whole thing plus the line integral going up, because that subtracts off the one going down, makes the line integral I want. Well, Green's theorem says I can evaluate the first one, since it's a closed path now, as df2 dx minus df1 dy, right? Or dg dx minus df dy, to use the other notation. And then I just have to evaluate this line integral along the real easy path right here and add it. So instead of three difficult paths, I just got an area over the plane region plus a line integral along this easy axis here. Well, the line integral over the region, df2 dx was 6 and df1 dy was 1. They were real easy. So the line integral over the region just turns out to be an easy one, which suggests this is a good approach. You get the double integral of 5 over the region. Pull the 5 out. This is constant. The line integral that's left coming down or going up the y-axis. We can write easy parametric equations for that. It goes from y equals 0 to y equals 27. So you just let y equal t and x equals 0. I wrote that in the last page. I forgot to point that out. You put, to go up the y-axis from 0 to 27, you put x equals 0 and y equals t, and let t run from 0 to 27. So I'll write it that way. Sine x of t plus y of t with the integram of sine x plus y dx plus 6x plus y dy. I replace the dx with dx dt dt and the dy with dy dt dt. And I have this integral to evaluate the line integral. But along that path, x of t, right, was equal to 0, y of t was t. And with x being 0, dx dt is 0. So this whole thing is 0 because it's multiplied by 0. Then x is 0, y is t. dy dt, since y is t along that path, so I told you it's an easy path. It's like y equals t and x equals 0. dy dt is 1. You just have to integrate 1 dt along the y-axis. So this method using Green's theorem is real nice. When you break it up, you just have an integral of a constant plus integral of a constant. Of t. Well, the integral of t is t squared over 2. You have to plug in the endpoints 27 and 0 and take the difference. The double integral dA, recall, is just the area of the region. So you've got 5 times the area of the trapezoid. Well, the trapezoid was easy because if you remember what it looked like, you could break it up into a square plus 2 triangles that were half of the square. The square was 9 by 9, and the 2 triangles were half 9 by 9 squares. So the area of the trapezoid was just 2 9 by 9 squares. So you get the area of a 9 by 9 square is 81. The area of 2 9 by 9 squares is 162. That's the area of R. Multiply that by 5, the constant outside. And then add this one, 27 squared over 2 gives you an additional fraction. And the whole thing just adds up to 2349 over 2. There is the line integral I wanted, that instead of doing 3 complicated line integrals, I just did a double integral of a constant over the region. plus a line integral down the easy y-axis. You can take your mic off and ask a question if you want. That's part of why we're doing this online. Let me know if you find anything difficult here. Oops. So this is a hard section. It's just because there's a lot of stuff in it. Here's another stuff. There's a vector form of Green's theorem that they try to stuff into the same section. So it's kind of like two sections. That's why we're taking 2 lectures on it this time. There's a vector form of Green's theorem for calculating flux in 2 dimensions. These line integrals are also very important in fluid mechanics, it turns out. The vector line integral we did before, integral f dot dr, in addition to calculating work, it will calculate circulation in fluid mechanics. What you do is this is a picture from this one, not what I'm talking about. When you calculate f dot dr, remember we said that that was calculating work. Maybe I should do it on the sideboard. Let's do this. Take a brief digression here. So now we had before that the line integral of f dot dr, the vector line integral, was defined to be the integral f dot t ds. This is a lot to swallow, I gotta admit, the last week or two. That was the way it was defined. This meant the scalar line integral of the scalar function f dot t. This is just an ordinary function, no vector components once you take the dot product. What is f dot t? Well, if you're going around a curve, let's make a closed curve because that's where Green's theorem is going to apply, but this applies generally. The idea is I'm going through a vector field, like a gravitational field or something. At each point, there's a gravitational force or something. And I want to calculate the work around here. At any point on here, maybe this is the force of gravity. How much work is gravity doing? What you do to calculate work is you take the component of force in the tangential direction. You take this one. If this is the force at the point, F dot the unit tangent gives you the projection of the force in this direction. It gives you the component of force. So what you're integrating here is the component of force moving along the path. That's what this is. Now change it over to fluid mechanics. Suppose F is not a force, but a velocity field. So this is, we'll still write F just because that's what we've been doing for line integrals. But now if this is the velocity of the fluid, F dot T is the component of fluid pushing you along in the direction of the path. And if you integrate around a closed path, the component of velocity that's pushing you around, we call this the circulation. And so this line integral is circulation. It's the amount of the velocity field that pushes the sum of the velocity field, in essence. You're integrating all the way around the path. The total velocity integrated around gives you what we call circulation. Now consider instead alternatively, suppose we were to take integral not f dot unit tangent ds, but f dot unit normal. We did this before for the unit normal, capital N, but for sticking with the book and lots of other books notations, let's use little n for what we used to call big N, the unit normal. Suppose I did this line integral along the curve, right? So this is the scalar line integral. Since I'm taking a dot product, I have a scalar function. And I call this one not integral f dot dr. Let's call it phi. Whatever this line integral is, we'll just give it a letter phi. And we'll just define it that way. What am I calculating here now? Well, now n is the unit normal. There's a unit normal, n. And if I take a vector and dot it with a unit vector, it is the projection. Remember, there's a nice projection formula that when you're projecting onto unit vector, all you got to do is take the dot product of the vector and the unit vector, and you get the projection. So this is the projection of f onto the unit vector little n. It's this component. It's the amount of the velocity of the fluid that's flowing outward from this curve. And so what you have when you integrate all the way around is you're calculating, essentially summing the amount of fluid per unit time flowing through the boundary. So flux is what we're going to call this. Fluid flux. It's the amount of fluid per unit time going through the boundary, because now we're integrating the component of this velocity field in the outward direction instead of in the pushing direction. So let phi denote this line integral f dot nds instead of the one we've come to know and love, and add another application. Suppose we want to know the flux. We want to know how much fluid per unit time is flowing out through the boundary. And then you can do this in 3 dimensions too. That's the part we're skipping at the end of the book for lack of time. It's not on the department syllabus even. But you can do this in 3 dimensions. I just wanted to point out there's something called the divergence theorem that does that. You want to look it up? All right, so if I make that definition, what can I do with that? Well, first thing I can say, we need the unit outward normal. If I put the normal in this direction, then I'm calculating how much fluid is going in, right? So we need n, the unit normal. What is it? Well, we know the unit tangent vector, and if we're doing the curve counterclockwise as required for Green's theorem, when you say the unit tangent in the direction that you're in the counterclockwise direction is, well, it's the tangent vector r prime divided by its length. Recall that? You calculate the unit tangent to a smooth curve by taking the derivative of the position vector divided by its length, because this is the tangent vector. Tangent vector over its length is unit tangent. Sorry to say that so many times. We need the normal vector that goes outward. Well, what you can do is just take this, take n to be the vector. Well, r prime is, when you write a parametric curve x of t, y of t, r prime is just x prime, y prime, and then you divide that by its length. Root x prime squared plus y prime squared. See, I got all that down. A perpendicular vector to that is easy. You just think for a second, you realize it's y prime over r prime minus x prime over r prime. How do I know this is perpendicular? Its dot product with this is 0, right? I take this times this and get x prime y prime over length of r prime, plus this times this is minus x prime y prime over length of r prime. So this dot this is 0. It's all divided by this, but it's still 0, right? So this dot this is 0. Furthermore, this is a unit vector because it's just got the same components of these reversed and with a minus. If you root sum square of these, you'll also get 1. So this is a unit vector that's perpendicular to this one. Oh, maybe it's the inward unit normal. How do I know if it's inward or outward? If you go counterclockwise, it's not, I'll wave my hands at this part, but you can show that this actually goes outward if this this curve is traveling counterclockwise. You could also use this one, and this would be the unit inward normal if you put the minus there. But, so here is the unit outward normal for a counterclockwise curve around a piecewise smooth closed path. Now we can evaluate this. Oh, not so easy, right? This is sometimes a very difficult integral. All right. Coming back here. This flux integral around the closed path, f dot n ds, can be rewritten like this. It's f dot n, which is a function of t. Right? If you write the parametric equation for the path as a function of t and integrate on the path t going from A to B, replace ds, recall, with r prime of length of r prime of t dt. That was ds before. And then, so well, what's f dot n? It's f1, f2, or little f, little g. We use both notations. Right? Dot x prime, y prime I'm sorry, y prime minus x prime is this one. This one has components f and g. This is the dot product. First component of this one times first component of the second one. Second component of this times second component of that. That's g times x prime over length of r prime. So this is the dot product of f and n. And then I've got the length of r prime dt. Now the length of r primes cancel. I just get fy prime minus gx prime dt, which by our theorem for evaluation of line integrals going backwards is actually equal to integral f dy minus t dx. Right? Replace y prime dy dt dt with dy and dx dt dt with dx. Going backwards on that evaluation theorem. Now Green's theorem applies. Right? Green's theorem says that integral minus g dx plus f dy, if I put it in the usual order. So this is the first component, this is the second component, is derivative of the second component with respect to x minus the derivative of the first component, which is minus g, with respect to y. It's this quantity, df dx plus g dy dA. So Green's theorem says this for this particular line integral. But now what's this? Maybe you remember what this is. This is what we call the divergence. We introduced the divergence before, which is del dot the vector field. And I should move this over one more time. And we'll just say now, by that argument we just did, the double integral or the line integral f dot n ds, the flux, we just showed is equal to the double integral of, well, we'll call it df, d little f dx. Let's write it in the other notation, or df1 dx plus df2 dy over the region enclosed. But this we said, I'm reminding you, is divergence. The divergence of a vector field f1, f2 was del dot f1, f2, where del is the gradient operator, ddx, ddy. Oh, it's just df1 dx plus df2 dy. So that was divergence. This is just the double integral of the divergence. So we have a new theorem that we just proved. You don't have to know that proof, but I thought you'd see when you want to see where it comes from. That says, is the vector form, they call it in the book, of Green's theorem. I'll call it a corollary here. A corollary is a theorem that, if it follows quickly from another theorem, you can call it a corollary. So it's up to you. I think this one follows quickly from what we just did there. So I'll call this theorem a corollary and say the flux integral f dot NDS along a closed curve around the boundary of a region is equal to the double integral over the region of the divergence of the vector field. This is a really significant result. It says the amount of fluid per unit time going out through the boundary can be evaluated by a double integral over the inside of the divergence. So the divergence somehow allows you to calculate how much fluid is going to go out. That's, that's the idea is it's incompressible fluid, so it pushes itself as much as it needs to out. And this has a nice generalization that we're skipping because we just the department syllabus, we don't quite finish the thing. We leave off a couple of applications at the end. And one of them is called the divergence theorem. There's a three-dimensional version of this called the divergence theorem that applies to surfaces bounding solids. And so this is for fluid going through the boundary of a plane region. The amount of fluid going out per unit time of flux is equal to this double integral over the plane region. I'll just say that this won't be on the final. We're not going to cover the section. But there's a similar theorem for the flux going through a surface of a solid is equal to the triple integral, actually, the divergence over the solid. So there's a one dimension higher version of this called the divergence theorem that you might want to look in your book. It's, I think, the last section in the book, actually. All right. Is it complicated enough? We're getting into the end of the book. Of course, it's complicated, right? Here's the last page. Let's use the vector form of Green's theorem for calculating flux. Well, I evaluate this line integral, f dot NDS, which I'm thinking of fluid mechanics here, how much fluid per unit time is going through a boundary in a plane region. Suppose F, the velocity field, is this. 3x plus y cubed is the component of velocity in the x direction. 9y minus x to the fourth is the component of velocity in the y direction. And suppose I want to know how much is going out this circle of radius 2 per unit time. Well, that can be a pretty complicated calculation to calculate integral f dot NDS around the circular boundary. But what the vector form of Green's theorem says is that instead of calculating that, I can calculate this double integral, oh great, double integral instead of a single integral, right, of the divergence. But this is a good idea because the divergence for this vector field turns out to be pretty easy, right? So sometimes this can make it harder too. It can make a hard double integral instead of a hard single integral. But for this particular vector field, maybe I need it up there for a second. Again, there it is. Remember the divergence is just derivative this with respect to x plus derivative this with respect to y. So derivative this with respect to x is just 3. Derivative this with respect to y is just 9. The divergence turns out to be easy. It's just a constant 12. Everywhere in the interior, the divergence of this vector field is just 12. So if I want to take the double integral of 12, I pull the 12 outside, I have double integral of the A is just the area. Boy, is that easy. It's area of a circle. Pi times r squared, pi times 2 squared. So I take 12 times pi times 2 squared, and I get 48 pi is actually the flux using the vector form of Green's theorem. All right, well, that's the last application, right? Pretty interesting stuff. I just want to make a couple comments then before we close. This is not for the final exam. Again, integral f dot TdS is called the circulation. That's the line integral we've been doing. It's also written as integral f dot dr. Now we said integral f dot dn is called the flux. Calculates the normal component of f. All these generalize to 3 dimensions is the point. And these are the couple of sections we're skipping right at the end. If you generalize these so that it's the amount of fluid flowing out through a surface per unit time, you can say the double integral over the surface, f dot n, d capital S, because it's big S for surface instead of little s for a path, arc length, is equal to the triple integral of the divergence of the three-dimensional field. So this is the divergence theorem, the one dimension higher version of Green's theorem, the vector form of Green's theorem. Now, furthermore, the other part of Green's theorem said that integral f dot dr could be written as df2 dx minus df1 dy, right? Remember that one? That was Green's theorem. Green's theorem itself extended to one more dimension. Suppose instead, we'll move this camera over. So higher dimensions. The vector form says that double integral over a surface, f dot unit normal d capital S, is actually equal to the triple integral of the divergence of f dv over the solid that's enclosed by the surface. I mean, the surface is sigma, for the vector version of Green's theorem. And then the line integral, the circulation along a path that moves in three dimensions, but it's closed, f dot dr. So this is for circulation around a 3D closed path. Has this nice interpretation. You can take the double integral of curl f dot n ds. Again, this is a surface integral, which is the section we skipped, where over surface sigma, where surface sigma, and you have to go counterclockwise again, by the way, for this to work. This theorem has the following picture. You have a surface sigma with this boundary down here. So here's sigma, this surface. And then it's got this boundary C. If relative to the normals that you pick, unit normals like this, you travel around the boundary counterclockwise, then the line integral along the boundary, calculating the work if F is a force, or calculating the circulation if F is a velocity field, can be evaluated by taking the double integral over the surface, sigma, curl F dot n. And then, if you think about it, Green's theorem applies to when this is a flat surface in the plane. You just did a flat surface in the plane, sigma. Two components of curl would vanish. And the last component would become df2 dx. So the last component of the curl is this, df2 dx minus df1 dy. You observe that Green's theorem is just a special case of this one that we call Stokes' theorem. Stokes' theorem generalizes Green's theorem, and when you take the special case of a flat plate in the xy plane, the curl becomes this, and it's Green's theorem. This one here is called the divergence theorem, we said. All right, so I wanted to have you see those at least because they come up in Maxwell's equations and electromagnetism, for instance, among other things. Next time, we'll just do review. So please take a look at the practice exam that I already put out. So you can download that. And please bring some questions. Any question on what we did today that you want to raise? We got just a couple minutes. I don't want to start the practice exam yet, but take a look at it and we'll go over that. That's the only thing we'll do next time. Thank you for your attendance.